Welcome! In this session, we'll tackle LeetCode problem number 1072, titled Flip Columns for Maximum Number of Equal Rows. This problem focuses on a fascinating matrix-based optimization challenge. We'll explore how flipping columns strategically can maximize the number of identical rows. Let's dive in and break this problem down step by step. In this problem, we are given a binary matrix where each cell contains either a 0 or a 1. Imagine that we have the ability to flip any column in the matrix. Flipping a column means changing all the zeros in that column to ones, and all the ones to zeros. Our goal is to determine the maximum number of rows that can have all their values equal, after performing any number of column flips. For instance, we might choose to flip one or more columns to align certain rows and maximize this uniformity. The input consists of a 2D array representing the binary matrix, and the output is an integer representing the maximum number of rows that can be made uniform after the flips. Let's look at the first example. We have a matrix with 2 rows and 2 columns. The input matrix is 0, 1, 1, 1. If we flip the first column, which is column 0, the matrix becomes 1, 1, 0, 1. Now, only one row, 1, 1, has all values equal. No matter which other columns we flip, it's not possible to make more than one row completely uniform. Therefore, the output in this case is 1, as that is the maximum number of rows that can become identical. In the second example, the input matrix has 3 rows and 2 columns, 0, 1, 1, 0, 1, 1. If we flip the first column, column 0, the matrix changes to 1, 1, 0, 0, 0, 1. Now, 2 rows, 1, 1, and 0, 0, are fully uniform. This is the maximum number of rows that can be made equal, so the output is 2. By carefully choosing which columns to flip, we achieve the best possible result in terms of uniformity across rows. Now, consider a larger example where the input matrix is 0, 0, 0, 0, 0, 1, 1, 1, 0. If we flip the third column, column 2, the matrix transforms into 0, 0, 1, 0, 0, 0, 1, 1, 1. After the flip, 2 rows, 0, 0, 1, and 1, 1, 1, become completely uniform. This is the best we can achieve, so the output is 2. The challenge lies in identifying which columns to flip to maximize the number of uniform rows. The problem comes with certain constraints. The matrix can have up to 300 rows and 300 columns, so it's important to design an efficient solution. Every cell in the matrix is either a 0 or a 1. Let's also consider some edge cases. For a single-row matrix, no flips are necessary since the row is already uniform, so the output is simply the number of rows, which is 1. For a single-column matrix, flipping that column will make all rows identical, and the output is the total number of rows. If all rows are already uniform, no flips are needed, and the output equals the number of rows. However, if all rows are different, we need to carefully analyze the flips to maximize uniformity, as seen in earlier examples. To solve this problem, the goal is to flip columns in a binary matrix to maximize the number of rows that become identical. One straightforward approach we could consider is brute force, where we exhaustively attempt every possible combination of column flips. This means evaluating all 2 to the power of n combinations, where n is the number of columns, and then checking how many rows become identical in each case. The combination that results in the maximum count of identical rows would be our answer. However, this approach faces a significant problem. The time complexity grows exponentially with the number of columns, making it computationally impractical for larger matrices. Specifically, the time complexity is 2 to the power of n multiplied by m multiplied by n, where m is the number of rows. This inefficiency renders brute force infeasible for real-world inputs with moderate or large dimensions. Now, to address the inefficiency of brute force, we turn to an optimized approach focused on grouping patterns. The key insight here is that flipping a column inverts the values in that column for every row. Instead of testing all possible column flips, we can reduce the problem to identifying patterns among rows. For 2 rows to become identical, their original patterns must either already match or match after one of them is inverted. For example, if one row is 0, 1, 0, and another is 1, 0, 1, flipping the first column aligns their patterns. The process involves calculating two patterns for each row, the base pattern, as is, and the inverted pattern, where all zeros become ones and vice versa. We then use a hash map to count the frequency of these patterns, and the highest frequency among them represents the maximum number of rows that can be made identical by column flips. The optimized approach is not just conceptually elegant but also significantly more efficient. The time complexity is O, m multiplied by n, where m is the number of rows and n is the number of columns. This is because we compute the patterns for each row, which takes linear time in relation to the number of columns, and then group them using a hash map. The space complexity is also O, m multiplied by n, to store the patterns in the hash map. This method is advantageous for large matrices as it avoids the exponential growth inherent in brute force. However, it does require careful implementation to ensure that patterns are computed correctly and edge cases are handled properly. While it sacrifices some simplicity for efficiency, this trade-off is justified by its ability to handle larger problem instances effectively. The chosen strategy for this problem is the optimized approach due to its vastly improved efficiency and scalability. By leveraging the insight that rows can be grouped by their patterns or their inverses, we eliminate the need to explicitly simulate column flips. Instead, we focus on finding the most frequent row pattern using a hash map. This results in a solution with a linear relationship to the number of rows and columns, making it both practical and performant. The trade-off here is that the optimized solution introduces additional complexity in terms of logic, compared to the brute force approach. However, given the exponential growth of brute force, the optimized method is clearly the superior choice. The key insight that flipping columns doesn't need to be simulated directly, but rather reduces to analyzing row patterns, is what makes this approach so effective. With a final time complexity of O, m multiplied by n, and space complexity of O, m multiplied by n, this solution balances correctness, efficiency, and scalability, making it the best fit for this problem. In this problem, we are given a binary matrix, and our goal is to maximize the number of rows that become identical after flipping some columns. Flipping a column means swapping all zeros to ones and vice versa for every row in that column. To solve this, we need to understand how row patterns change after flipping. Specifically, two rows can be made identical if their patterns align either directly or by flipping the same set of columns. This brings us to the concept of equivalence. Two rows are considered equivalent if one is identical to the other, or if one is the bitwise complement of the other. Instead of flipping columns in every possible way, which would be computationally expensive, we can optimize the process. By representing each row in a canonical form, its original state or its complement, we can count how often each form occurs. This allows us to identify the maximum number of rows that can become identical efficiently. To implement this, we use a dictionary to store the frequency of each canonical form, and tuples to represent these forms since they are immutable and hashable, making them ideal dictionary keys. The algorithm begins by initializing a frequency map, which is simply a dictionary to count how often each row's canonical form appears. Next, we iterate through each row in the matrix. For each row, we compute its complement by flipping all bits, changing zeros to ones and ones to zeros. Then, we determine the row's canonical form, which is the smaller of the row and its complement when compared lexicographically. We increment the count of this canonical form in our frequency map. Once all rows have been processed, the largest value in the frequency map tells us the maximum number of rows that can be made identical by column flips. The result is simply this maximum frequency. The key operations here include calculating the canonical form, which ensures equivalence is handled correctly, and efficiently updating the frequency map using dictionary operations. This approach avoids the need to explicitly flip columns, saving computation time. In terms of complexity, iterating through each row and computing its complement takes O, n, time per row, leading to an overall time complexity of O, m asterisk n, for a matrix with m rows and n columns. Space complexity is also O, m asterisk n, in the worst case, where we store all unique row patterns in the dictionary. To better understand the algorithm, let's walk through an example. Consider a matrix with 3 rows, 0, 1, 0, 1, 0, 1, and 0, 1, 0. For the first row, 0, 1, 0, its complement is 1, 0, 1. Comparing these, we find that 0, 1, 0 is lexicographically smaller, so it becomes the canonical form. For the second row, 1, 0, 1, its complement is 0, 1, 0. Again, the canonical form is 0, 1, 0. Finally, for the third row, 0, 1, 0, the complement is 1, 0, 1, and the canonical form remains 0, 1, 0. After processing all rows, we have consistently mapped all of them to the canonical form 0, 1, 0. At this point, the frequency map contains a single entry, 0, 1, 0, 3. This tells us that all three rows can be made identical by flipping the appropriate columns. The maximum frequency in the map is 3, which is the result of the problem. This example highlights how the algorithm efficiently reduces the problem to counting canonical forms instead of explicitly trying all possible column flips. Now, consider some edge cases. If all rows are already identical, no flips are needed, and the result is simply the total number of rows. If every row and its complement are unique, the maximum frequency is 1 since no two rows can be made identical. For an empty matrix, there are no rows to process, so the result is 0. The final implementation of the algorithm ties these steps together. The implementation begins by using a dictionary from the collections module to create an empty frequency map. For each row in the matrix, we calculate its complement and determine the canonical form by comparing the row with its complement. The frequency map is updated for each canonical form. Finally, the maximum value in the frequency map, which represents the highest count of equivalent rows, is returned as the result. This approach works because it avoids redundant computations by focusing on canonical forms instead of flipping columns explicitly. The use of a frequency map ensures that we can efficiently track and count equivalent rows, and the linear complexity in terms of rows and columns makes the algorithm scalable for larger matrices. By reducing the problem to its core mathematical properties, the solution is both elegant and efficient. The solution for LeetCode problem number 1072 flip columns for maximum number of equal rows is implemented using a normalized pattern-based approach. #explanation. 1. Goal: we aim to maximize the number of rows in the binary matrix that are identical after flipping some columns. A column flip inverts all entries in that column, 0 becomes 1 and vice versa. 2. Key insight: for two rows to become identical after flipping, their patterns must be either the same or exact opposites. For example, 0, 1, 1, and 1, 0, 0 can align if we flip the first column. 3. Approach: for each row, calculate two patterns. Base_pattern, the row's original structure. Flip_pattern, the row's structure after flipping, inverting, all its values. Count how many times each pattern, or its flipped version, appears across the matrix. This is done using a counter to store pattern frequencies. 4. Steps: for each row in the matrix, calculate both base_pattern and flip_pattern. Increment the frequency of both patterns in the counter. Finally, return the highest frequency recorded in the counter, which represents the maximum number of rows that can be made identical. 5. Complexity. Time complexity, O, m*n, where m is the number of rows and n is the number of columns. This is due to iterating through all rows and computing the patterns. Space complexity, O, m*n, in the worst case for storing all unique patterns. This solution is efficient and avoids unnecessary brute force computation by focusing directly on possible row patterns and their flipped equivalents. In this Java implementation, we first import the necessary classes and define the max_rows_after_flips method inside the solution class. The goal here is to determine the maximum number of rows that can be made identical after flipping some columns. To achieve this, we use a hash map called patternCounts to store the frequency of each row pattern. We then iterate through each row of the given matrix. For each row, we construct two string representations, the base pattern, which is the row as is, and the flip pattern, which represents the row with all values flipped, ones become zeros and zeros become ones. These patterns allow us to group rows that can be made identical by flipping columns. After constructing the patterns, we update their counts in the patternCounts map using the getOrDefault method to handle cases where the patterns are encountered for the first time. This ensures we track the occurrences of both the base and flipped patterns effectively. Finally, we calculate the maximum number of rows that can be made identical. We iterate through the values in the pattern counts map, which represent the frequency of each pattern, and use the math.max function to update the max rows variable with the highest count found. Once we have the maximum count, we return it as the result. This value represents the largest number of rows that can be made identical after optimally flipping columns. With this approach, we efficiently compute the solution by leveraging pattern matching and frequency counting, ensuring that the algorithm handles the problem in a clean and concise manner. To solve the problem, we begin by analyzing a simple input matrix with two rows, 0, 1, and 1, 0. First, we initialize an empty counter called patterns to keep track of the occurrences of each row pattern and its flipped version. Now, for the first row, 0, 1, we treat it as our base pattern and convert it to a tuple, resulting in 0, 1. Next, we calculate its flipped pattern by flipping each bit in the row, which gives us 1, 0. We then update our patterns counter to account for both the base pattern and the flipped pattern. At this point, both 0, 1, and 1, 0 have been seen once, so the counter reflects this with a count of 1 for each pattern. Currently, the patterns counter is updated to show that 0, 1, and 1, 0 each have a count of 1. We now move to the second row of the matrix, 1, 0. Here, the base pattern is 1, 0, and the flipped pattern is 0, 1. Again, we increment the counts for both patterns in the counter. After processing this row, the patterns counter is updated to show that both patterns, 0, 1, and 1, 0, have been seen twice. Finally, to determine the maximum number of rows that can become identical after flipping columns, we look for the highest value in patterns.values, which is 2. Therefore, the output for this example is 2. Next, let's consider a scenario where all rows in the matrix are identical. The matrix has 3 rows, all of which are 1, 1. As before, we initialize an empty counter patterns. For each row in the matrix, the base pattern is 1, 1, and the flipped pattern is calculated as 0, 0. Each time we process a row, we increment the counts for both the base pattern and the flipped pattern. Since all rows are identical, the counter reflects that both patterns, 1, 1, and 0, 0, have been seen 3 times, corresponding to the 3 rows in the matrix. At this point, the patterns counter shows that 1, 1, and 0, 0 both have a count of 3. To determine the maximum number of rows that can become identical after flipping columns, we find the maximum value in patterns.values. Here, the maximum value is 3, which means all 3 rows can be made identical. Therefore, the output for this example is 3. Now, let's move on to a case where the rows in the matrix are mixed rather than identical. We now analyze a matrix with 3 rows that are not identical, 0, 0, 1, 1, 1, 0, and 0, 0, 1. As before, we start by initializing an empty counter patterns. For the first row, 0, 0, 1, the base pattern is 0, 0, 1, and the flipped pattern is 1, 1, 0. We increment the counts for both patterns in the counter, resulting in a count of 1 for each. Next, we process the second row, 1, 1, 0. Here, the base pattern is 1, 1, 0, and the flipped pattern is 0, 0, 1. After updating the counter, both patterns now have a count of 2. Finally, we move to the third row, 0, 0, 1, where the base pattern is again 0, 0, 1, and the flipped pattern is 1, 1, 0. For the third row, we increment the counts for both the base pattern, 0, 0, 1, and the flipped pattern, 1, 1, 0, in the counter. At this point, the patterns counter shows that both patterns have been seen 3 times. To determine the maximum number of rows that can be made identical after flipping columns, we find the highest value in patterns.values. This value is 3, which means 3 rows can be made identical. Therefore, the output for this example is 3. To analyze the time complexity of our solution, let's break it down into its key components. First, we iterate through all the rows in the matrix. If the matrix has m rows and n columns, this initial iteration takes m time. Next, for each row, we normalize it by constructing 2 patterns, the base pattern, which is simply the tuple representation of the row, and the flip pattern, which involves flipping each bit in the row and then converting it into a tuple. Constructing a tuple for a row of length n is n, and flipping the elements also takes n. So, normalizing a single row is O(n) plus O(n), which simplifies to O(n). When we process all n rows, this normalization step contributes O(m*(n) to the total time complexity. Finally, we update a counter dictionary with these patterns. Since dictionary insert and update operations are O(1), on average, updating the dictionary for all m rows takes O(m) in total. These steps lay the foundation for understanding the time complexity of the solution. Building upon the earlier steps, we now examine the process of finding the maximum frequency from the counter. This involves scanning all unique keys stored in the dictionary. In the worst-case scenario, the dictionary can contain up to 2 to the power of n unique patterns, as each row generates both a base and a flip pattern. Iterating through these keys to find the maximum frequency takes 2 to the power of n. Now, combining all the components, the normalization and dictionary updates contribute O(m*(n), and finding the maximum frequency adds 2 to the power of n. Therefore, the total time complexity of the solution is O(m times n plus 2 to the power of n. This complexity remains consistent across best, average, and worst cases, as every row must be processed, and the maximum frequency must always be calculated. This makes the solution efficient compared to a naive approach, which we will discuss shortly. Let's now turn to the space complexity. The most significant contributor is the patterns counter, which stores occurrences of unique base and flip patterns. In the worst case, all rows generate unique patterns, and each pattern is a tuple of size n. Storing one pattern requires n space, and with up to 2 to the power of n unique patterns, the patterns dictionary can occupy 2 to the power of n*(n) space. Additionally, for each row, we temporarily create 2 tuples, the base pattern and the flip pattern. These tuples collectively contribute m*(n) space when considering all rows. However, since they are not stored permanently, they don't add to the peak memory usage. Finally, the input matrix itself requires m*(n) space. When we consider all these components, the dominant factor is the space required for the patterns counter, and this gives us a clear picture of the memory usage in the solution. When we combine all the space requirements, the total space complexity is primarily determined by the storage of the patterns counter, which is 2 to the power of n*(n). While the input matrix also requires m*(n), this is typically smaller than the space required for the patterns. Therefore, the overall space complexity is 2 to the power of n times n plus m times n. Now, comparing this to a naive brute force approach, we observe significant efficiency gains. A naive method would involve flipping each subset of columns and checking if all rows are equal after every flip. This requires processing 2 to the power of n subsets, and for each subset, checking equality across m rows takes m*(n). As a result, the time complexity of the naive approach becomes 2 to the power of n times m times n. The space complexity, on the other hand, remains m*(n), since it only needs to store the input matrix. While the naive approach is computationally expensive, understanding its limitations helps highlight the effectiveness of the optimized solution. In contrast, the optimized solution avoids directly flipping columns by leveraging the concept of patterns to normalize rows. This significantly reduces the time complexity to m times n plus 2 to the power of n. While the space complexity increases to 2 to the power of n times n plus m times n, due to the storage required for the patterns counter, this trade-off is acceptable because it allows us to achieve a much faster runtime. For large matrices, this optimized approach is far more practical, as it minimizes the computational overhead while efficiently handling the problem's constraints. By focusing on patterns instead of brute force column flips, we achieve a solution that is both elegant and scalable, making it a robust choice for tackling this problem. When solving this problem, there are a few common mistakes to watch out for. One major issue is not normalizing rows before comparing them. Remember that rows should be treated as equivalent if they are complements of each other, for example, 1, 0, 1, and 0, 1, 0. Without normalizing these rows, you might end up comparing them incorrectly and reach the wrong conclusion. Another common pitfall is using an inefficient brute force approach. Trying every possible combination of column flips results in exponential complexity, which becomes computationally expensive and impractical as the matrix size grows. Also, edge cases like matrices with all zeros, all ones, or single-column matrices can lead to errors if not handled carefully. Finally, overusing nested loops instead of leveraging more efficient data structures like hash maps can lead to unnecessary inefficiencies. A well-thought-out approach avoids these traps by optimizing for both correctness and speed. It's also important to consider the constraints of the input. Ignoring factors like the size of the matrix or the number of rows and columns can lead to overly complex solutions that don't scale well for larger inputs. A key insight for this problem is that rows that can be made identical are either already the same or exact complements of each other. This simplifies the task to counting equivalent row patterns after normalization. A hash map is an excellent tool to efficiently group and count these normalized row patterns. For normalization, you can use the first element of each row as a pivot. Flipping the row if the first element is 1 ensures consistent comparison across rows. Additionally, in an interview setting, it's important to explain why this hash map-based solution, with its O and *m complexity, is superior to brute force. Emphasizing its scalability and real-world applicability can set your solution apart. This problem shares similarities with other challenges, so understanding related problems can deepen your grasp of the concepts. For instance, LeetCode 890, Find and Replace pattern, involves grouping strings with similar transformations. Similarly, LeetCode 451, Sort Characters by Frequency, leverages hash maps to count occurrences efficiently, and LeetCode 1331, Rank Transform of an Array, highlights the importance of normalization for comparison. Another related problem, LeetCode 721, Accounts Merge, focuses on grouping data based on equivalence relations. When considering alternative approaches, brute force is one option where you try all possible column flip combinations to identify the maximum number of identical rows. However, this approach is computationally expensive, with exponential complexity, and is unsuitable for large inputs. On the other hand, the hash map with normalization approach is optimal. By normalizing rows using the first element as a pivot and grouping equivalent patterns, you achieve a solution that scales linearly with the matrix size, making it far more efficient. Another approach worth mentioning is the use of bitmask representation. Here, instead of working with rows as arrays, you represent each row as a binary number. This allows you to perform column flips using bitwise operations, which can be quite memory efficient for small matrices. However, while this method can reduce memory usage, it is less intuitive and can be harder to implement correctly, especially when ensuring consistency across rows. It requires a solid understanding of bitwise operations and careful attention to detail to avoid errors. While it's a viable alternative, its complexity and implementation challenges make it less suitable for general-purpose problem-solving compared to the hash map method. To summarize, we solved the problem by leveraging hash maps to group rows based on their flipping patterns, achieving an efficient solution. Key takeaways include understanding symmetry in binary matrices and mastering the use of hash maps for pattern grouping. Thank you so much for watching, and don't forget to like and subscribe for more problem-solving tutorials. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!